So next we'll discuss row equivalence. So here's a definition that we'll fill in. Two matrices A and B, so that's what we start with. We start with two matrices A and B. They are said to be row equivalent if the following statement holds. And here's the statement. I'm just going to put a bracket there. So this is the statement here. That is the defining statement for the definition of row equivalent. So two matrices A and B are row equivalent if you start with the matrix A, there's some sequence of row operations that you can perform one after another to end up with the matrix B. Now sometimes this will be true and sometimes it'll be false. It depends what the matrices A and B are. But in the case where this statement is true, if it is possible to carry A to B through a sequence of elementary row operations, then we say that A and B are row equivalent. Okay, so there's a few things you can say about this. If you start with any fixed matrix A, so in the first remark we're going to start with a matrix A and say it's fixed in the background. And remark 1, and I'm going to read this in a little bit different of an order than it's written down, but I promise you what I'm saying is exactly equivalent to what's mentioned in the first remark. But if you have a matrix A that's fixed in the background, there is a unique matrix R which satisfies two properties. 1, it's in reduced row echelon form, and 2, it's row equivalent to A. And in this case, R is called the reduced row echelon form of A, right? If there's a unique matrix R that satisfies both of those conditions, we can give it a name, and that's why we do. So we call it the reduced row echelon form of A. So we'll take advantage of this abbreviation. Reduced row echelon form of A. Really, that's this matrix R. We didn't call it R in the past, but that's really what you're looking for when you perform row operations to solve an augmented system. That's why say you and I both are solving the same system of equations, and we both write down an augmented matrix, and we both do row operations to carry it into reduced row echelon form so we can write down the general solution of the system. This remark is saying that the reduced row echelon form that I get and the reduced row echelon form that you get are going to be the same. Unless, of course, one of us made a mistake. But if neither of us made a mistake, we're both going to get the same result. So that's what remark 1 is really saying. And the second remark is actually going to give us a way to characterize row equivalence without mentioning elementary row operations. Remember what elementary row operations correspond to? We talked about it on the previous page. They correspond to elementary matrices. If you take any row operation, there's an elementary matrix that corresponds to that row operation. To get it, just do that operation to the identity, and then you'll get the corresponding elementary matrix. So if you know the size in advance. So let's write down the rest of this statement. So A and B are row equivalent if and only if. Now, if we were to just go up with it by the definition, the statement would A and B would be row equivalent if and only if A can be carried to B through a sequence of elementary row operations. Well, how about we take that sequence of row operations and identify each of those row operations with an elementary matrix, and we can realize the performance of those elementary row operations as left multiplication by the elementary matrices. So that's the idea here. So let's fill in the statement. So if and only if, here's the statement. There exists, we're going to word this carefully, there exists elementary matrices. Now, how many of them will there be? We don't really know, because in the definition of row equivalence, there's no limit on how long this sequence of row operations could be. There might be 7 row operations, or there might be 70 row operations, or there might be 170 row operations. It might be very long. We don't really know. So we have to stay general. We don't know how many row operations there would be. So if we were going to write down a correspondence between each of those elementary row operations and their corresponding elementary matrices, we don't know how many matrices we're going to have. So we have to stay general here. So how about we just do this? There exists elementary matrices E1, E2. We're going to make a list all the way up to EK. And I'm going to use the letter K as a stopping index because I don't really know how many there are in this list. So if there's 20 row operations, then there's going to be 20 elementary matrices here. If there's 30 row operations in that sequence, then K would be 30. Right? That we're just staying general. So there exists elementary matrices E1, E2, all the way up to the last one, EK, however long that list may be, such that you can write B is equal to E1, E2, all the way up to EK, times the matrix A, where this is just a string of multiplication. So you take the matrix A, first you multiply it by EK on the left, and whatever you get on the rest, whatever you get as a result, you'd go down the next in the chain. Maybe EK minus 1, you'd multiply that onto the result of EK times A, then whatever you get for that, you'd go down to the next one, and so on. You just multiply every one of the matrices in this long string by A on the left, one after another. And that's really the same as effectively performing those row operations. Because remember, on the previous page, we talked about the fact that if you take an elementary matrix that corresponds to I pointed to the wrong point on the page. If you take an elementary matrix that corresponds to a row operation, and you multiply another matrix by this elementary matrix on the left, you have the effect of actually performing the corresponding row operation on the right-hand factor. So that's what we're taking advantage of here. This is really just another way of phrasing the definition of row equivalence, but we're just doing it in terms of elementary matrices instead. Okay, this is going to become useful later. The third remark is that, remember when we talked about invertibility, we did mention early on that not every matrix has an inverse, right? Not every matrix is invertible. Well, elementary matrices are nice in the sense that they're all guaranteed to be invertible. And this remark tells us that, and it also tells us how to get the inverse. So let's read this carefully. All elementary matrices are invertible. And in particular, that just means you're going to say something more specific than the previous statement. If E is the elementary matrix corresponding to a particular row operation, well then E inverse is the elementary matrix corresponding to the inverse of that row operation. So whatever this row operation was here, the row operation that corresponds to the elementary matrix E, take the inverse of this row operation, which is what's mentioned down here, and that's going to be the elementary row operation that corresponds to E inverse. This is a lot to unpack when you first see this remark, but it's actually not saying all that much. But when you look at it for the first time, it could be a little bit intimidating. So let me give you an example of what this would look like in a specific case. So here's an example of an elementary matrix. Take a 2x2 matrix that has ones along the main diagonal, and a 2 in the upper right corner, and then a 0 in the bottom left corner. That is an elementary matrix. And how do I know that? Because it corresponds to a single elementary row operation performed on the identity matrix. So let's draw that correspondence. This corresponds to what? What would I have to do to the 2x2 identity matrix to get this back as a result? Well, if I took the 2x2 identity matrix and I add row 2 to row 1 twice, that would have the effect of introducing this 2 here. So this corresponds to the row operation. Row 1 is replaced with row 1 plus 2 row 2. That's the correspondence between this elementary matrix and this elementary row operation. Now, in this remark, we mentioned something called the inverse of the row operation. Well, what would the inverse of a row operation be? Let's talk about the inverse of this row operation. So I'm taking row 1 and I'm adding row 2 twice. Well, the inverse of that operation would be to, instead of adding row 2 twice, just subtract row 2 twice. And they're inverse operations in the sense that if you were performing some row operations on a matrix, and you first did this operation, and then you did this operation immediately afterwards, they would cancel each other out. But you would, if you did this one first, then you did this one, it would undo the work that the first one did. So these are inverse operations. That's the first thing we'll observe. Now, what this remark is saying, first of all, is that this elementary matrix is, because it's an elementary matrix, it's guaranteed to be invertible. And also what the remark is telling us is that a way we can find out the inverse of this matrix is to first convert it to a row operation, find the inverse of that row operation, and then since this is an elementary matrix, we can find since this is an elementary row operation, we can find an elementary matrix that corresponds to it. So let's just do the same thing I did above, but in reverse. Let's convert this to an elementary matrix. What would the elementary matrix be that corresponds to this operation? Well, to find out, just perform this operation on the 2x2 identity matrix. If you have the 2x2 identity matrix and you take row 1 and you subtract row 2 twice, what you're going to get is this. okay, you're going to get this matrix, right? If I have the 2 by 2 identity and I do this operation, I'll end up with this. So what this remark is saying is that we can complete this chain and say these are going to be inverse matrices, or matrix inverses of each other. So let's write matrix inverses. And since these are 2 by 2 matrices, you can check that directly if you want, and I'd invite you to do so. Just use the 2 by 2 inverse formula for matrices. Remember what it is? If you have A is, let's say A is the matrix A, B, C, D, and you have the inverse formula A inverse, which is 1 over AD minus BC, then you're going to swap the entries on the main diagonal and put a negative on each of the other 2 entries. And you can check that if you plug this matrix into this formula, you're going to get this matrix. So that's what this remark is saying, that if you follow this diagram for any elementary matrix, you can always get its inverse. Okay, so this is also going to be very important when we study something called the inversion algorithm, which is going to be the main result of this section.